Thank you, Andrea. So before I start the talk, I would like to really thank the marvelous generosity and his availability. He has been sharing all this. So it's wonderful that the organizer of this conference. Okay, so this is a work done with Omer Aksoy, who is in the audience. He's attending the conference the whole month, and Apoorv Tiwari, who was a postdoc with me and is moving to Sweden for another postdoc. And they are really brains behind this talk. So this talk has two results that I formulate as a theorem, as theorems. And the first, so let me flash the results first, and then I will motivate, I will go for motivation, and then I will try to prove those theorems to you. The first theorem states that for any d-dimensional Majorana lattice Hamiltonian, call it H, such that H is local, H has a symmetry, and the symmetry group is the translation symmetry group, a direct product with a group called GF, where GF is a fermionic symmetry. So it knows about the conservation of fermion parity. Third assumption is that H has a non-degenerate, symmetric, and gap ground state. And then with those three assumptions, we're going to see that an even numbers of Majorana degrees of freedom per unit cell must be present in the system. So the unit cell is this rectangular color in red here, and it repeats itself in a translation invariant way. And the symmetry group is the translation cross GF, and I put it underneath the underbrace, and the underbrace is covering the whole system, which is translation invariant. So that's the first theorem. And the second theorem has a little bit different structure, as you see from the drawing, but I will explain the drawing. So let me state the hypothesis and then the conclusion. Now we limit ourselves not to d-dimensional Majorana lattice Hamiltonians, but to one-dimensional Majorana lattice Hamiltonians. Again, assumption one, this Hamiltonian is local. Assumption two, we have this G translation direct product GF symmetry. We have where now GF is a fermionic symmetry, but it is more than that because it is internal. It is well defined on every repeat unit cell that I represent by a rectangle colored in blue. So the GF is now repeated under every repeat unit cell, and it is above the underbrace that represents the entirety of the system, the chain. Hypothesis 3 is that H has a non-degenerate, symmetric, a gapped, and now you could say it's a ground state, but I'm going to be more precise. It is an even or odd parity injective fermionic matrix product state, which is a ground state, so by assumption. So I'm not saying it is any ground state, I'm saying it is a FMPS ground state that is either even or odd, of either even or odd parity. And when I make this hypothesis, that when I restrict myself to FMPS state, then I can prove rigorously that GF is realized by a trivial projective representation. So the keyword here is, there are two keywords, trivial and projective. And I will explain when we go through the proof what I mean by trivial projective representation. And that's the main result of today's talk. Let me state a contraposition to this theorem. I'm going to negate the conclusion and get the negation of one of the hypotheses. And that would be an equivalent version of this theorem. So if I consider a one-dimensional Hamiltonian H made of Majorana, where H is local, admits the global symmetry group as in hypothesis 2, But now I am realizing with GF a non-trivial projective representation, so the opposite of the trivial projective representation, so a non-trivial projective representation, then H cannot have, it's a no-go theorem, H cannot have a non-degenerate gapped and symmetric ground state that can be described by an FMPS state. So the contraposition of theorem 2 as stated is a no-go theorem about the impossibility to realize a gapped unique matrix product state, ground state that is symmetric. So some comments about those results. So this theorem doesn't assume that I can realize GF on a repeat unit cell represented by the red rectangle, but I can realize GF once on the whole chain. Okay. So I cannot call GF internal symmetry, on-site symmetry, but then the statement follows. And if I have an even number of Majorana degrees of freedom per unit cell, then I am allowed then to construct an internal symmetry. Yes, I'm going to explain. So that comes. So some comments about the statements, the two claims that I am making. So the thermodynamic limit is implicit in both theorems. The direct product structure of the symmetry group G translation direct product GF. So this direct product here, this is crucial. So those two claims, those two theorems break down if you don't have this direct product structure between G translation and GF. This can happen if you have magnetic translation symmetry group, for example. Theorem 1 holds in any dimension without any restriction on the harmonic symmetry group GF. Theorem 1 for one-dimensional lattices can be proved with the help of Theorem 2. So if you have Theorem 2, you can prove Theorem 1, but that's not the way I'm going to do it. Fifth comment is that GF so far is arbitrary, so it can be continuous. But it can be that for a continuous group, its projective representation on the local Fock space can be trivial. That's for Theorem 2. If so, essentially the contraposition of Theorem 2 is not predictive. Okay, so if you have a trivial representation, whether or not you have a unique non-degenerate ground state, you don't know. You cannot use you don't have enough information. However, you have other means, you have other tools available to you to decide if you have a non-degenerate unique ground state or not. For example, you can use, when you have continuous harmonic symmetry group, you can use complementary arguments such as adiabatic threading of a gauge flux. We saw this type of argument last week. And of course, Oshikawa used this type of argument to generalize ieb-Schultz-Mattis theorem to higher dimension. So the full power of Theorem 2 is unleashed when GF is a finite group. That's where this theorem is really useful. A weaker form of the Theorem 2 holds in any dimension if it is assumed that the harmonic symmetry group GF is abelian and can be realized locally using unitary operators. I didn't specify if my symmetry, symmetries are to be represented anti-unitarily or unitary. I can do it, but to extend the proof of Theorem 2 to higher dimension, I have to weaken the value of the theorem by making a stronger hypothesis. And those are the two hypotheses that I am making when I want to generalize Theorem 2 to a higher dimension. Actually, I'm not going to give, in this talk, I'm going to give you the proof of Theorem 2 and 1 in higher dimension. And so for the rest of the talk, you can always assume that, or you have to assume that GF is abelian and represented unitarily. So I'm not going to give you the proof. You can find it in our paper, the proof in 1D with matrix, determinic matrix product states, because I find it technical, and I found the proof that I will present in this talk more intuitive. And also it's a bit more powerful because it applies to any dimension. So now, to answer your question, Andrea, I like to review what is the ieb-Schultz-Mattis theorem. So it's a theorem that was written up in a paper written by Schultz-Mattis in 1961. And the question they were after is the search for an analytical argument that could decide if the nearest neighbor antiferromagnetic quantum spin 1/2 Heisenberg chain supports antiferromagnetic long-range order at 0 temperature. So in 1961, people didn't know if you have long-range order or not. They knew that it was impossible by 1966, but that was 5 years later. So they could not answer this question rigorously, but what they could show rigorously is A, that if you go in the XY limit of the SU2 symmetric chain that I'm considering now, then you have a gapless spectrum with all correlation functions of spin decaying algebraically in space. That they could show. And that was the main result of their paper, but they had appendices. And their appendices contain some theorems, one of which is now called the ieb-Schultz-Mattis theorem. So the two appendix that you can find in the two theorems in the appendix of the ieb-Schultz-Mattis paper of 1961, the first one states that the ground state of the nearest neighbor antiferromagnetic quantum spin 1/2 Heisenberg chain made of an even number of n of sites is annihilated by the total spin operator. So this is a spin singlet. And this is true for an even integer number of sites. Next, and that's what is called now the ieb-Schultz-Mattis theorem, is the nearest neighbor, so it's the same Heisenberg spin chain with an even numbers of sites, when obeying periodic boundary conditions, supports an excited eigenstate with an energy of order 1 divided by the number of sites above the non-degenerate ground state for any even integer n. Okay, so they were able to construct a state that was orthogonal to the ground state and had an energy of order 1 over n. The distance in energy to the ground state was of order 1 over n, where n was even in the length of the chain for an SU2 symmetric nearest neighbor Heisenberg, well, I mean, the canonical Heisenberg spin 1/2 chain.
Chris, could I ask something? On the previous page, equation 1, or the first theorem, is also true only when n is even. It's hard to see how it would work when n is odd. No, sorry, on the page you were just talking about. What you called theorem 3.
Theorem 1 requires n. So theorem 1 requires n to be even, because I want to be able to construct a fermionic Fock space globally. So I need an even for theorem 1.
Okay, thanks.
And then for theorem 2, I don't have to specify that because my repeat unit cell has an even numbers of Majorana by hypothesis, because I can realize GF on a repeat unit cell. So it means that I have an even numbers of Majorana per blue rectangle. Hence, I have an even numbers of Majoranas in the system. So I'm good in that respect. So I think that actually, I mean, for the first theorem, I need an even numbers of repeat unit cell. For the second one, I actually forgot. I'm not sure, but I don't think I'm not sure. But the reason why I require an even numbers of sites in the ieb-Schultz-Mattis theorem for spin chain is because if you have an odd numbers of spin chains, your total spin is going to be 1/2, and you have degenerate ground states.
Okay, thank you.
Okay, so I stated the ieb-Schultz-Mattis theorem to give you a context. And let me make some comments, 4 comments about the theorem. So the original proof of the LSM theorem does not apply to the nearest neighbor antiferromagnetic quantum spin 1 Heisenberg model. So when the spin is 1 instead of, so if it is an integer, well, 1, you cannot prove, the proof doesn't go. So where is the breakdown of the proof for spin 1? Well, it is still possible to show for s equal to 1 that there exists a state with an energy of order 1 over n above the ground state for any n, which is, here I don't think you have to worry about evenness or oddness, but however, it is not possible to show that this state is orthogonal to the ground state. Second comment, ieb-Schultz-Mattis only proved the existence of at least one excited state with an energy that collapses like 1 over n to that of the ground state in the thermic limit. So this state might not be isolated, so we don't know that. So that if you don't know if it is isolated, so if it is the bottom of a continuum that collapses to the ground state, there is no guarantee that the thermic limit of the ground state and this excited state are distinct. So neither the existence of a gapless continuum of states nor the degeneracy of gap ground state in the thermic limit have been shown in the ieb-Schultz-Mattis theorem. Originally, ieb-Schultz-Mattis make use of the global SU2 symmetry of time-source symmetry in their theorem, but I will explain that those are not necessary assumptions. Now, you could also ask, so I asked in the first comment, what if the spin was integer or spin 1 as opposed to spin 1/2? It doesn't work. What if dimension is larger than 1? So the variational state that the ieb-Schultz-Mattis constructed, you can construct it in any dimension, but the energy separation that you get with the ground state is scaling like n to the d-2, which is not good, which is only useful when d is equal to 1, but for any higher dimension, it is a useless bound. So the proof doesn't go for high dimension. Their proof, their attack, I mean, their strategy doesn't work in any but one dimension. So you kind of, okay, so the theorem was there, people knew about it, but I think there was an acceleration in the interest for this theorem in the 80s that arose from Haldane's conjecture that half-integer spin chains and integer spin chains behave very differently at long distance. So half-integer spin chains are supposed to be gapless, or I mean, they are gapless. That's an established fact now, at least empirically or using numerical diagonalization. And integer spin chains, nearest neighbor, et cetera, antiferrometric spin chains, they are gapped. So Affleck and Lieb in '86 revisited the LSM theorem and improved on it. So the improvement were that they could treat any spin S that was a half integer, not only 1/2. They relaxed the condition, the hypothesis that you had an SU2 symmetry, so you could put a magnetic field so that you still have a uniform magnetic field will break the SU2 symmetry down to a U1 quantization axis, rotations about a quantization axis that would give you a residual continuous U1 symmetry. And they wanted to have translation invariance. So those are the hypotheses. And they could see, they could show that with those hypotheses, the ground state is non-degenerate for any finite chain made of an even numbers of sides with a gap again that collapses algebraically like 1 over n to the ground state. In the thermic limit, they could not tell the difference between a scenario whether by which you had degenerate gapped ground state or you had non-degenerate and gapless ground state. So there they have problems controlling the thermic limit. So 11 years later, Oshikawa, Yamanaka, and Affleck replaced the condition of Affleck that the spin S has to be non-integer to establish this result by the condition that you replace the spin by the magnetization, the total magnetization of the system along, which is a conserved quantity because we have a U1 rotation symmetry that survives divided by the numbers of the length of the chains. So this coefficient nu equal to to those two numbers on the right-hand side of this equation here, this coefficient nu, if it is not an integer, then the theorem goes. The prediction, the predictive power of the theorem applies. So at this point, people were looking at spin chains, but Yamanaka, Oshikawa, and Affleck in '97, the same year as the comment 2, applied the same strategy to deal with interacting Hamiltonians of electrons, provided that the Hamiltonians as well are local. And then you just replace nu, that was mz divided by n plus the spin s. You conserve this, you replace this by the filling fraction, the numbers of fermions divided by the numbers of repeat unit cell, capital N. However, all those papers so far has always assumed that reversal of time or inversion symmetry in space were good symmetries. And this is not necessary assumption either, as shown by Koma in 2000. So the most recent version of the ieb-Schultz-Mattis theorem is due to Tazaki in 2018. And let me take you through the steps that he's using to establish a theorem that is much more powerful than all the previous theorems so far. So now what he does in the first step is so there are 3 steps in his proof. The first step is a construction of variational states. And I stress that there are not one variational state as before, but there are many of them. So there is a boldface plural form of states. Second, the energy expectation values of these variational states are shown to collapse to the ground state energy in atomic limits. Third, the variational states are shown to be orthogonal with each other and with the ground state for any fixed numbers of degrees of freedom. And these conditions, and the conditions under which this orthogonality survives the atomic limit is given. So let me go back. I colored comment 1, 2, and 3 into red, magenta, and blue, and let me refine a little bit what is done in those 3 steps. So in step 1, what you do to construct your variational states is you take the ground state. He doesn't demand that the ground state is unique in his proof. He doesn't only demands that the ground state is an eigenstate of translation operator, but it doesn't have to be unique. And then he takes this ground state and he hits on it with an operator that smoothly distorts the ground state. And this smooth deformation, it's done locally. So at every repeated cell, you deform a little bit the ground state. And this deformation is essentially by gauging the global continuous symmetry that he has, symmetry. So instead of doing a global U1 symmetry operation, he does a resolve in space rotation, U1 rotation by a tiny bit on every repeat unit cell. So it is in this construction, it is essential to have a continuous symmetry in order to make this perturbation, this distortion to this variational state to be a smooth, a small perturbed version of the ground state. It's very essential that the symmetry group the internal symmetry group is a continuous one. So now you see what you do is that actually the twist he does is a 2π twist. Actually, this is the same thing that was done by ieb-Schultz and Mattis, but ieb-Schultz-Mattis did their twist over the whole length of the chain. But what Tazaki does is that he does it on a finite segment of the chains. So he twists by 2π, but if this segment over which he does the twist is very long, then the twisting from one repeat unit cell to the other is going to become very, very small. And with the smallness of the twist from one between two consecutive repeat unit cell, you get the energy expectation value to be also very small for this variational state. So now you can control smoothness and the closeness of this variational state to the ground state as measured by energy expectation value. Now, when you estimate the energy of this variational state, you have a Hamiltonian and you want to look at the expectation value of this variational state And then what you have to do is that you have to bound this expectation value somehow. And it's very crucial that the Hamiltonian is local, because it's made of local. On every repeat, you need cellular terms to be bounded. And so you have a control on the sum of all those terms. And in this way, you make sure that you have a bound that is to the ground state, to the variational state energy, that is a ground that is going to be under control. So locality comes in an essential way when you want to show that the variational state collapses in energy to the ground state. Now, he can do that, and that's the difference with the previous works. He constructs a variational state in a segment of the line here, a segment of the line not overlap. So he can do it at many, many different times under control. And all those states, variational states, are going to be orthogonal to each pairwise, and they will also be orthogonal to the ground state. So then he can decide what is the fate of those variational states in the thermodynamic limit. In fact, what he does is that he gives conditions for to have gap degenerate ground state in the thermodynamic limit. And the conditions that he finds is that either you have spontaneous symmetry breaking of translation symmetry, in which case you have finite degeneracy. But if you preserve the translation symmetry of the lattice, and you cannot break in one dimension the continuous symmetry by Mary and Wagner, so the only thing you can do is break spontaneously the translation symmetry. That's one option. But if you don't break this symmetry, then he shows that in the thermodynamic limit, you have an infinite degeneracy of the gapped ground states. Infinite, no finite degeneracy. Of course, the proof of orthogonality in the first states hinge on the filling fraction nu not being an integer value number, and the existence of translation symmetry in addition to the continuous symmetry. But the proof of orthogonality only use this information from the Hamiltonian. You don't have microscopic, you need no more information from the Hamiltonian to establish orthogonality than this filling fraction and the existence of those symmetries. So proving orthogonality in some sense is much easier than proving the collapse in energy under control in a controlled way in the thermodynamic limit. So the contraposition of the extension of Tazaki's ieb-Schultz-Mattis theorem is that if the ground state manifold is finitely degenerate and separated by a gap from all excited state in the thermodynamic limit, then either translation symmetry is spontaneously broken, or nu, the filling fraction, is an integer. So that's an equivalent way of stating the result of Tazaki. And I want to stress that you cannot, if you don't break spontaneously translation symmetry, you simply cannot have finite degeneracy of the gap ground state manifold. And this is tantamount of saying that under his hypothesis, you cannot have something like topological order. We're on a torus, but finite degeneracy without breaking any of the protecting symmetries is impossible. So this is a specialized version of a no-go theorem for topological order in one dimension. So now the questions that we want to address, the new result that we want to present in this talk is, can we dispose of the assumption that the symmetry, the fermionic symmetry, is continuous? Can we work with discrete symmetries? And can this discrete group accommodate the conservation of fermion parity? I.e., can I work with Majorana? And that's the content of the two theorems that we gave. So let me now give you the proof of theorem 1 in any dimension, and then I will do, yes?
Sorry, can you give some sort of simple picture in terms of fermions of this theorem or generalized form of the theorem? What is your intuition about?
You asked me what type of fermionic Hamiltonians fulfill the conditions of Tazaki's theorem?
Yeah, so
Hubbard model.
Hubbard
model.
Hubbard model. Yeah, but
any Hamiltonian in one input that you can have fermions. Is not an integer, and as long as you have a hopping that and then you have U1 symmetry. Lecture doesn't work. Where distribution of charge will work if the hopping is finite range, and if and that's it. it's completely general. It's to the Hamiltonians, the Hubbard model. So you need the U1 symmetry. In a spin system, it's natural to, if you have, you start with SU2 and then you have, you put a uniform magnetic field, then you'll have U1. That's enough. And the U1 for fermions is simply charge conservation. So global gauge invariance. Or other, I mean, it doesn't have to be charge conjugate, charge conservation. It could be another U1 that you have.
Well, I admit my ignorance, but I mean, if we speak in terms of fermions, like Hubbard model,
yeah,
what's the point of having an infinite degenerate ground state?
No, this is well, I said either you break spontaneously translation symmetry, or if you don't, you have a situation of infinite degeneracy, which is very pathologic.
Yes.
Yeah.
So you have to break translational invariance.
You have nature chooses to break translation symmetry usually, right? Or you could break if GF had the. I mean, okay. So is that what they are saying is what I wanted to say is that a situation where you have a symmetric ground state that is gapped, degenerate with a finite degeneracy. This is not possible. I think that's more. I think the examples of infinite degeneracy are many, but you cannot have an open chains and then there will be no degeneracy, and then you have you put it on a torus, a one-dimensional torus, and you have a finite degeneracy without breaking the symmetries and without and with a gap, which is usually one way of defining what is topological order. So a degeneracy that depends on the topology. So since I mean there are in the talk of Alex, he had tensor interpretation of this result, Pep's interpretation of this result, I think. So you have different, but I mean it is contained in Tazaki theorem with his hypothesis. But okay. So now I restate the theorem again. I have my repeat unit cell colored as a rectangle in red. It repeats itself. I have a translation symmetry, G translation. So I put Peric boundary conditions. And I take the direct product with a fermionic symmetry group GF because I'm dealing with Majorana. I do not assume a priori that the numbers of Majorana per red box is even, but I do demand that the total numbers of box is even, so that I'm sure that I have a total numbers of freedom that is, so that I can define a Fock space, a fermionic Fock space. I want to have that. Now I drew it in one dimension, my lattice, but the proof applies to any dimensions, D. So H is local. H has translation direct product GF symmetry. By assumption, I make the assumption that the ground state is non-degenerate, symmetric, and gapped. Then my claim is that there must be necessarily, we must have an even numbers of Majorana degrees of freedom per repeat unit cell. So how do I prove that? So the proof goes by contradiction. So I assume that I have an odd numbers of Majorana degrees of freedom per repeat unit cell. And we'll see that there will be a contradiction with the first three assumptions. One of them, at least, yeah, the assumption of degeneracy, the non-degeneracy assumption will break down, as we will see. So I consider a D-dimensional lattice, and I use the notation boldface J for a site of my lattice lambda. For every J, it is labeling my red rectangular box. There is a Majorana spinner with 2n+1 components. So the Majorana spinner is chi Majorana spinor is chi j, but index L runs from 1 to 2n+1. That's the flavor, the color index, the internal index of my Majorana. By assumption, lambda has cardinality which is even. And now the trick of the proof is the following. You are familiar with periodic boundary conditions. So in 2 dimension, if I start on this side here, then I go like that, and then when I am here, I jump back to this one here, and I do this for all cycles that are along the axis of the torus, and I close the torus using this jump here. So that's conventional periodic boundary conditions, but I'm going to do something different. I'm going to use tilted boundary conditions. So the translation group is this translation group if I have this picture here. But instead of using this translation symmetry group, I'm going to use this tilted one here. And the tilted one here is the following idea. I start from here, I go down, down, I hop, I translate this site like that, like that, like that. And when I'm here, instead of going back to the blue site where I started from, I jump to the next blue site along the J2 axis. And then I continue like that. So my path colored in red on the figure on the left is going through all sides of the two-dimensional lattice that is wrapped along a torus. But this path is actually defining, is defining a cyclic translation symmetry group, which is Z indexed by the cardinality of my lattice, and not by the direct product of the direct product of d different Z's indexed by the linear size in the d dimensions of my d-dimensional lattice. So I will establish a result for Hamiltonians that have a symmetry under tilting translation. Then I will have to argue why the result that I prove for those type of Hamiltonians are relevant to the conventional Hamiltonian with obeying periodic boundary conditions. And this step is not rigorous. But if I have this symmetry, translation symmetry group, everything is rigorous. So in terms of Majorana spinors, the total fermion parity operator P is simply the product of all my Majorana modes, my Majorana operators. So first, I fix the repeat unit cell J. Then I take the product over the internal degrees of freedom L. They run from 1 to 2n+1, and I take the product over all the J's. Now, the generator, I have one generator of my tilted translation symmetry group. I call it T1. I only have one. And then I can conjugate parity by T1. And now you have to trust me. But when you do the conjugation, you can pass the T1 minus 1 on the right to the left of P, so that it gives you the identity with T1 here at the cost of -1 to the power absolute cardinality of the lattice -1. Now, by assumption, the cardinality of the lattice is even. So cardinality of even number -1 is odd. -1 to the odd number power odd is minus. So I get this anti-commutation relationship. So now I will write down a little bit more precisely the Hamiltonians that obey those tilted boundary conditions. But the point is that now what I have is that I have two operators that are commuting with my Hamiltonians, but they anti-commute pairwise. And that's like a Kramer degeneracy. It implies a degeneracy that is at least twofold for every energy eigenvalue in the spectrum, which is a contradiction with our initial assumption that we had a non-degenerate ground state. This algebra 5, this anti-commutation between parity and translation, the tilted translation operator, this was a result obtained in 1D by Xie in 2016. And it gives you de facto a degeneracy associated to quantum mechanical supersymmetry. Now I have to justify why the difference between periodic boundary conditions and tilted boundary condition is conjectured to be irrelevant in determinate limit. And this conjecture goes back to Yahoo and Oshikawa, who wrote a paper in the past few months before us, and a paper that helped us enormously in trying to derive those results. So we drew all of our inspiration from the Yahoo and Oshikawa paper written in the long past, a few months before ours. So they argue why, they give an argument, and it's not rigorous. That's why the theorem applies, if you want, to Hamiltonians obeying the tilted boundary conditions, the tilted translation symmetry. That's rigorous, but there is a hole in the argument, and the whole of the argument is similar to the hole in the argument when I can prove to establishing rigorously that the energy goes to zero in the thermic limit. So the energetics, we don't have a rigorous control of it. That's a hard problem, as usual in physics. But this problem that this result that we drew is is just algebra that use a minimal set of information from the Hamiltonian. So I rely on Yao and Oshikawa to justify the fact that I can jump from Hamiltonians that obey this tilted translation symmetry group to periodic ones.
Christopher, just a question.
Eduardo?
Oh, hi, long time no see. The tilted boundary conditions, isn't that equivalent to say that you have states with a finite momentum of order 1 over n?
A finite what?
Momentum, linear momentum, compared to the periodic boundary conditions.
I don't know. I don't know.
It's equivalent to a translation of momentum in the sense of the, it's an analog, if you wish, of the,
The answer is that I don't know, but yeah, so that's
it looks like you're acting essentially with a linear momentum operator, and
yeah, well, so the Hamiltonian we're looking at is, I mean, the difference between Hamiltonian obeying twisted boundary conditions and one obeying periodic boundary conditions, it's a numbers of the only difference between the two Hamiltonians is along the cuts here. So if it's this, you cut here, and then you cut here, and you change the blue lines into the red lines. So the two Hamiltonians differ by a sub-extensive numbers of terms. So that's good news. So that makes it plausible that in the thermic limit, this difference is not catastrophic. And Yao and Oshikawa give an argument. Well, I will state precisely the conjecture they make, and in their paper you will find a transfer matrix argument substantiating their conjecture. But I think it's the honest answer is it is a conjecture, and and I don't have. I mean, it is kind of counter. I mean, we are not doing one-dimensional physics in these guys, right? That's not what we are doing. But it is, we change quite dramatically the cyclicity of the. I mean, the G translation in free. Is polycyclic, and in two the translation group is a simple. It's just a cyclic group. So okay. So that's the best I can say. I don't know the answer to your question. I can only cross my fingers and hope for the best.
I have a answer. I suggest an answer that if this lattice would have been space-time lattice,
yeah.
Then what Eduardo says would be right. You would get an energy in the ground state due to the twist in the boundary condition, but this is space. So this energy is extensive only with respect to one direction, not with respect to the volume. So it's small. Doesn't have there is an energy, but is extensive in a lower dimension. So it goes to zero.
That's why I'm saying intuitively, we are messing up. We are changing the two Hamiltonians by a sub-extensive numbers, which is the boundary defined by shifting.
Yes.
But I think okay. So we are changing a sub-extensive numbers of terms in the Hamiltonian. But we also made the assumption that the ground state is unique. So what could go wrong? I don't know. I think nothing, but who knows? But that's the assumption that we are making. So now I go to the theorem 2. I have 10 minutes to go, and hopefully we'll be on time. So now the only difference between, well, the setup is a little bit different because I am, well, actually, you can see the logic now that I have shown that to have a unique ground state, a non-degenerate ground state, I have to assume that I have an even numbers of Majorana per repeat unit cell. Then I can make this assumption because in my set of assumptions 1, 2, 3, the third one is assuming non-degenerate ground states. So I know that theorem 1 tells me that I must have an even numbers of Majorana in my blue repeat unit cell, and hence I can define GF in a completely consistent way, its action on my blue repeat unit cell. So this is what I call initial symmetry. People call it on-site symmetry. I can put the GF above the underbrace for every little repeat unit cell. So now the statement is the proof in 1D doesn't need to assume that the group is abelian and it is unitarily represented. But the proof that I'm going to present using tilted boundary conditions, so not only tilted, but twisted as well, this proof only works presently if we assume that the GF is abelian and unitarily represented. And I will comment on that at the end. But now the statement is that if you want to have a non-degenerate symmetric and gap ground state, GF must be realized by a trivial projective representation. And I will explain now how this, what I mean by trivial projective representation. So let's go through the machinery. So my notation is I have my lattice lambda, I impose periodic boundary condition. I can define a Fermionic Fock space locally for every repeated cell because I have even numbers of Majorana. And then once I have my local Fock space, by tensoring, I have my global Fock space. And now the group GF, I'll just be a bit more precise. What is the group GF? It is technically called a central extension of a group G by Z2F, where Z2F is the notation I use for fermion parity. So now the point is that the group GF is not necessarily the direct product of G by Z2F. It can be more than that. It doesn't have to be. So essentially, we are looking, if you're giving me G, the group, and Z2F, fermion parity, GF, the central extension, is kind of all the possible ways of making a new group out of two groups, G and Z2F. But now I'm assuming that whatever the outcome of gluing G and Z2F is, this outcome GF is assumed to be abelian and realized by unitary operators. I stress that this is only needed for the proof to work in higher D, but in 1D with Fermionic matrix product state, I do not need to make those assumptions. Okay, we have translation symmetry, and we have, if we use periodic boundary conditions, we have the polycyclic group in equation 7. So more precisely, if I hit a Majorana on the repeat unit cell J with my translation, my generator of translation along a mu direction, I just shift J by the lattice basis vector E mu. If I impose, because I impose periodic boundary conditions at the level of operators, I have this identity. So if I square T mu to the power N mu, which is the numbers of lattice sites in the direction mu, then I get the identity operator. So I'm given a G in the group GF.
Sorry, you mean you get the identity when acting on the ground state, because you could have states which are not translation invariant.
I'm sorry. No, so that's periodic boundary condition. So this is correct.
So for all states, you're going to demand that this is the identity.
So that's how to implement periodic boundary conditions on a torus.
Yeah, okay.
So now I choose G in my Fermat group, an element of my Fermat group, and I want to represent it. And what I mean by my definition of an internal symmetry is simply that the representation of capital U of G is the tensor product, or the direct, the tensor product of little UJs. So capital U is acting globally, and it's obtained by simply tensoring the action of a little UJs. So the rule is that locally, E, the neutral element of GF, is the identity operator on my local Fock space, Germanic Fock space. But now, what I mean by projective representation of the group GF is the possibility that when I multiply the representation of G by the representation of H locally, I get the representation of GH multiplied by a phase that depends on the group element G and H. And this exercise has to be done consistently, by which I mean that associativity 10C should be correct. And as Alex explained yesterday, this implies he had the omega yesterday here. I have an exponential, his omega is my exponential of I phi. And my function phi, which is a function of two variables on the group GF, has to obey this rule here. This CG is, by our assumption that we only deal with unitary representation, CG is always equal to 1. But if I work with anti-unitary representation, CG can be -1. That's a possibility, but so in 1D, when we do the proof in 1D, we don't set CG to be equal to 1. So you see that even though GF is abelian, its realization at the quantum level might not be if the function phi is not symmetric in its two arguments. So now I assured you that there was the possibility to have a phase in the representation of the group multiplication table of GF. And then the question is this phase, can I gauge away this phase? Can I gauge away this phase? So how do I do that? So phi, the phase that I acquired, it's a function from GF cross GF into the interval 2 pi. And the question is whether I could gauge away the effect of phi. And gauging is done as follows. You take, you ask if there exists a function psi of GF into the interval 0 to pi, such that phi and phi prime only differ by this combination of psi's. So if there exists such an object psi, which is a function of a group to the circle, then you say that phi and phi prime are equivalent. They are gauge equivalent. And then now the question is whether phi is gauge equivalent to 0 everywhere on the group. So the condition 11, that was the conditions, the compatibility with associativity for the projective phase that we are allowing in 10B. This condition has a name in mathematics, and it says that we are looking at functions of GF cross GF into 2 pi that are two cocycles. And now, whenever when you have a phi that is a pure gauge, you call it a two co-boundaries. And because we look at the equivalence relationship up to gauge equivalence, then you look at the quotient of the two cocycles to the two co-boundaries, and this quotient space is this object here, which is the second cohomology group. So 2 refers to the fact that phi is a map from GF to GF, from GF cross GF to 0 to pi. The entry GF is because it tells you what group you have here. And then the second entry of this parenthesis is simply the target space of this map here, which is U1 here. The C refers to the possibility that I have anti-unitary transformations, which I have not by assumptions, but I kept the notation. So by convention, the neutral element of the second cohomology group corresponds to a group representation of GF, because the phase can be gauged to 0 everywhere. And that's what I call a trivial projective representation. So a trivial projective representation is when my quantum mechanical representation of the GF symmetry group is a faithful, is one-to-one. It's a homomorphism all over that. We are safe. Okay, so now I have defined precisely what I mean by trivial projective representation, which enters in the assumption of the theorem. And let me now simply, so the total symmetry group is equation 13, translation times GF. And now what I do is that I take a polynomial h of j. It's a finite order polynomial in Majoranas. And all the Majoranas are appearing in h of j. They are all, you know, they can be around j. They don't have to be in the same unit, repeat unit cell, but the polynomial is finite. And so it means that because my polynomial is finite, I guarantee locality. And so I can choose any j, and then I just can translate with my generators of my polycyclic translation group. And by construction, this Hamiltonian has a translation symmetry on the torus. But if I demand equation 14b, namely that hj is the same as hj after conjugation by the global symmetry group U of j for all j's, then I have I have a symmetric Hamiltonian under G total. But now instead of solving the problem of this Hamiltonian, what I do is that I'm going to cheat, and I'm going to establish a rigorous result for Hamiltonian 15, where what I do now is define a family of Hamiltonians that depends on G on the left of this equation in 15. And I have two index on H, tilting. We have already encountered tilting. That's the path that goes, that's this one-dimensional path that goes along all the sides of my lattice in D dimensions. And twisting means that on this, when I am going from here to here, I act with a group, a local group element. So I like with little u of j when I go on the when I close the loop from here to here. So that's what I do. So this is what this tilted twisted Hamiltonian is, and by construction, this has a translation symmetry, the tilted translation symmetry group, but it also commutes with all global representation of the Fermionic symmetry group. So all U of H commute with H tilted. So you need to, this is not obvious, you have to calculate, but if you calculate, you'll see that U of H commutes with H tilted and T1G, which this is obvious by construction. So now, if this Hamiltonian 15 has a ground state that is non-degenerate, which is symmetric with respect to the tilted twisted translation symmetry operation and gap, the same could be true of H Peric boundary conditions, because the two Hamiltonians only differ by sub-extensively many local terms in the termic limits. So if this assumption holds, then if I can prove theorem 2 to H tilt twist of G, then I have proven my theorem to H periodic boundary conditions. And of course, this statement I cannot prove, but I can assume that it is reasonable. So now the idea of, so here I have defined, this is just a formal definition of what I said in words. So when I look at the action of T1G under Majorana operator J, conjugation by T1G of chi J, if J is not equal to the last site in my one-dimensional path before going back to the first site, then the only thing I get is a phase factor, because I have to, you know, chi is it's an odd Fermionic. I mean, I have to account for the Fermionic grading of my Fock space. So rho of G is just telling you if G, if the representation of G anti-commutes with the Fermion parity operator. So if it does, you know, so it's just keeping track of Fermi statistics if you want. But when you go for, when you're on the last site, before jumping on the first site of this long, winding, tilted, one-dimensional path, you do this. You have a local action here. This is not capital U, this is a local U that is acting on the last link, if you want, of my one-dimensional path. So this is like threading a flux via one hopping matrix element, so to say, on a torus. So now we repeat what we had done before. So we take T1 to the n, and T1 to the n, when there is no G here, or when G is the neutral element, it's simply the identity operator, but now it is not anymore the identity operator when G is not the neutral element. So that's the difference. And then the crucial thing is that now if I conjugate T1 G with U of H for any pair G and H, I find a phase chi. Now this phase chi is related to the phase phi that defines the projective representation, plus the effect of fermionic grading in my Fock space. So this equation 17c reduces to the results of Yao and Oshikawa that applies to bosons, to spin systems. So this term is gone, but the difference with for our calculation is that we deal with Majoranas and we have this extra term. Now this phase chi is gauge invariant under the gauge transformation that I defined previously. And now you can show that for chi to be 0, you need to have phi to be trivial. So chi is identically 0 if and only if phi is trivial. That you can prove. It's not trivial, it's non-obvious fact, but it is so. And so you see that if it is not trivial, then you have this non-trivial phase in 17b, which means that you have two operators that commute with the Hamiltonian, but pairwise, they don't. So translation symmetry, the generator translation symmetry does not commute with U of H for a pair G and H if this chi G of H is not equal to 0 identically. And this immediately implies that if this phase chi is not 0 for all G and H, then it means that the spectrum cannot be the ground state, or there must be a degeneracy of the ground state, which is a contradiction to our assumption. So we have proven the theorem. And now I have to close the loop. So Yao and Oshikawa in their paper state that when a local quantum many-body Hamiltonian with lattice translation invariance and a global continuous or discrete symmetry has a gapped spectrum with a non-degenerate ground state under periodic boundary conditions, the same must be true under any symmetry twisted boundary conditions. So their paper contains they say it's a conjecture. They are honest, but they give an argument which is actually what you said. They try to quantify the error that you make when comparing the two Hamiltonians, and they use the sub-extensive difference between the two Hamiltonians to argue that that the difference is irrelevant in your atomic limit. But there it is quite crucial, I think. It's transfer matrix, and you need to have a highest Lyapunov exponent, a unique Lyapunov exponent. So you need to have a unique ground state, I think. Okay, so now I'm late by time. So this transparency is just telling you why things go sour when you demand that you try to generalize this result to non-abelian groups and for non-unitary representations. So we jump over that. And this is the construction that we did for the tilted, twisted boundary conditions, and that's the summary of the talk. So I don't repeat, you have seen the theorem twice at least stated. So I'm done with my talk, and I thank you very much.
Questions, please.
I have a question. Where in your proof do you need the fermions to be Majorana? Why they cannot be just Dirac? Because an even number of Majoranas is equivalent to, can be an odd number of Diracs, okay? the way the Lieb-Mattis-Schultz theorem is presented is that you have an even, if you have an even number of fermions, meaning of complex fermions, then the ground state can be gapped. It's trivial. So isn't there a period 4 condition? Okay, so instead of 2.
So Eduardo, I must confess, your voice has a low frequency, and via Zoom,
okay, so let me try.
I never understand.
Let me try again. Yes, my students complain about my low frequency voice.
No, but I think
long after they stop being my students. Okay, that's okay. No, the question here is the following: where in your arguments do you need the fermions to be Majorana? As opposed to,
because if I had complex fermions, I don't need. Tazaki has done everything for us.
Okay.
So if I don't break charge, so when you break charge conservation, you're in trouble. You cannot use the U1 symmetry that Tazaki uses or Lieb-Schultz-Mattis relies on. So that's why I repeated the argument of Lieb-Schultz-Mattis, because I wanted to stress that the variational state is obtained by. So they do the hard work. They really estimate the energy cost to creating the variational state. So they do energetics. But the reason why the energy cost is so small is a bit like a Goldstone theorem. You use the continuity of the symmetry group so that you twist, when you go from one lattice side to the other one, the twist is very small.
Correct, yes. Correct. Thank you.
So that I don't have at my disposal anymore. If I deal with if I have superconductors, if I'm in a P wave, I mean, if I'm in class D, I'm screwed.
Thank you.
More questions?
Yes. Is there anything known for space group symmetry, like inversion, reflection, maybe in addition to?
Yes, I think it is. So Shinsei, we did the simplest thing, but I think the answer is yes. But the answer, I don't know how to do it, of course. But I think it is possible. Yeah.
I again admit my ignorance, and I don't get the corresponding ideas in quantum field theory. So, well, is this is not related to spontaneous symmetry breaking, right? It is related to the fermionic.
I can. You're wondering if you wasted 1 hour of your life listening to me. So the point is that I think the philosophy here is to try to understand what are gap states of matter. I mean, there is the no-go version of the theorem. I mean, originally, Lieb-Schultz-Mattis wanted to understand why the spin 1/2 chain, according to Bethe and that, was gapless. And they found a condition that applies for spin 1/2, but for spin 1, their argument breaks down. And in fact, for spin 1, the spin chain is gapped. So you can take the contraposition of their theorem, and it tells you when the system has a non-degenerate ground state that is gapped. So then condensed matter physicists started getting interested in gapped phase of matter, and you too, because you care about topological field theories.
Yes.
So the Lieb-Schultz-Mattis theorem, or their extension, is a way to, depending on how you formulate it, is a way to tell you under what conditions the ground state of some Hamiltonian will be non-degenerate and gapped. And if or not you break the symmetries available that are present in your Hamiltonian. And now I can make a connection to, because of your question, you see, here I'm dealing with yesterday we talked about SPT phase of matter. There is a close connection between this result that I present now and the Alex result of yesterday, because my classification of my projective representation somehow, when to have the prediction is that one way to get a non-degenerate ground state is to have a trivial representation. Mm-hmm. So I have a trivial representation of algebra, but now I ask the question, what happens if I open the periodic boundary conditions and I look at the boundary? Mm-hmm. And it turns out that then I can fractionalize my trivial projective representation of the bulk.
Mm-hmm.
And the fractionalization is exactly the same cohomology class.
Mm-hmm.
So if I look at, the cases where I have a non-generated ground state that is symmetric, that doesn't break any of the protecting symmetries, then I can ask, I open the system, I look at the boundaries in 1D, and then I ask in what ways, what happens to the boundaries on the boundary? How does the algebra that I had in the bulk, which was trivial, how is it projected to the boundaries? And what I'll find is that this information, I mean, I will use the same language and the same technology to decide when I have SPT phase.
Mm-hmm. Okay. Just
okay.
I'm wondering if these are related to the global anomalies that you said yesterday. So that this state can, if there is an anomaly, this can be exist only on the boundary or in higher dimensional.
Well, I think here what we define anomaly is when we say that the theory is anomalous when the on-site representation is non-trivial.
Yeah.
So that's our definition of anomalous.
Yeah, that's why I was wondering if it is ieb-Schultz-Mattis is the lattice version of this kind of field theory stuff. He says yes, maybe.
Omer knows more than me. I don't know. Okay. You know, Eduardo, I am ashamed that I don't know what a 't Hooft anomaly is. It seems to be very popular those days. I'm still stuck with the Carroll anomaly. And,
yeah.
So do I. Don't worry. Okay.
Okay. Thanks.
People like to use too many words for the same thing. So it's just okay.
Can I
please
leave?
please.
No, can I finish because I'm tired?
Okay, so we thank again the speaker, and we have we are ahead of time. We are a bit late, but okay, let's reconvene in 5 minutes. Okay.